The foundation of the entire physical chemistry series includes the 6 quantum mechanical postulates and the laws of thermodynamics. In quantum mechanics, every single particle is a wave that can be described by a wave function psi of the position of the particle r and time t. R has 3 components, x, y, and z, in the 3 directions of the 3-dimensional universe. A wave function may not have any physical meaning, but the squared modulus of a wave function is the probability density of finding the particle at the position r at time t. Now imagine the air density, which is equivalent to this psi squared of a particle. So imagine this air density may change with the altitude and time when you climb Mount Rainier. So what is this squared modulus? The squared modulus of a wave function is equal to the wave function multiplied by the complex conjugate of that wave function. And what is complex conjugate? The simplest way to get the complex conjugate of a wave function psi is to replace every single I with negative I, where I is the square root of -1. This means the complex conjugate of a real function is itself. At any given time t, we have the integral of the probability density of a particle over the entire space from -infinity to +infinity equals 1. This simply means the probability of finding that particle in the entire space at any given time is 100%. Now the 6 postulates. Postulate 1. The wave function must be single-valued, continuous, and finite. This is to ensure the probability of finding the particle is single-valued, continuous, and finite. In postulate 2, for every observable, such as the position or momentum of the particle, there is a corresponding operator. So over here, the position, you may have the position x, y, and z with a corresponding operator x with a caret on top, y with a caret on top, and z with a caret on top. What's the corresponding operation? It's very simple. If you apply this x operator to a function, it's simply that function multiplied by x. In the momentum operator here, px, py, and pz, again also with a little hat on top. And then what's the example here? If you apply this px momentum operator to a wave function, for example, this is a complex function e to the power of -ikx. And then we simply do the first derivative of this wave function, and then multiply by this -ih bar. What's the result? The result is k times h bar. I'm sorry that I made a mistake here. I forgot to put this explanation function here and also here. How about the momentum in the y direction and z direction? They're similar. Over here it's -ih bar, and then followed by this delta over delta y. Basically, you just need to take the first derivative of the wave function and then multiply the result by -ih bar. So with the momentum operator, we can derive the kinetic energy operator. Remember, the kinetic energy is half mv squared, which is equal to p squared, the momentum squared, divided by 2m. So if you use these operators, square them, and sum up the squared of each momentum in each direction, you will get this expression for the kinetic energy operator. Again, this is the kinetic energy in the x direction, y direction, and z direction. Over here, I'm giving you a very simple example. If I have a wave function x plus y plus z, and I know its kinetic energy is 0, it's because if we take the second derivative of this wave function, it's going to be 0 in each of the 3 directions. potential energy. So this is the notation in classical mechanics. This is the notation in quantum mechanics, simply with a caret on top that indicates this is our operator. And sometimes we use V as the potential energy. Potential energy is usually the function of the position of the particle, and that's x, y, and z. And then if we apply a potential energy operator to a wave function, that's equivalent to this multiplication between that wave function and the potential energy function. What about the total energy? The total energy is equal to the kinetic energy plus the potential energy. So for a particle, it's just the sum of the kinetic energy in the three directions and the potential energy this particle feels. Angular momentum. In classical mechanics, usually people use L sub x to denote the angular momentum along the x direction. And then in quantum mechanics, again, we put a caret on top, and this is the operation. We simply apply this operator to the wave function of interest. And why is that? It looks very complicated, but in classical physics, we have this angular momentum is equal to the cross product of the position vector and the momentum vector of the particle. And this can be expressed as a determinant with the first row as the unit vectors in the three directions, I, j, and k, and then we copy this x, y, z in the second row, px, py, and pz in the third row. So x, y, z, px, py, pz are all scalars. But the result is going to be a vector. So if you know how to evaluate a 3 by 3 determinant, it's very simple. It's just this I multiplied by this 2 by 2 vector, yz, py, pz. So over here, and then minus j times also a 2 by 2 vector here, and then k times the third 2 by 2 vector, x, y, px, py. So over here. And then we can expand this 2 by 2 vector. Very simple. It's y times pz minus z times py. So we got this expression for the angular momentum in classical physics, but in quantum mechanics, we'll have to put a little hat on top of pz and py and px. And then we have to expand this px, py, pz into this negative IH bar times delta over delta x, or delta over delta y, or delta over delta z. That's why we have this more complex expression as the operator of angular momentum in the x direction, in the y direction, and in the z direction. Now, postulate 3. So if we try to measure a observable quantity, for example, the position or the momentum or kinetic energy with a corresponding operator O, the only values that will ever be observed are the so-called eigenvalues of the operator O, which satisfy this eigenequation. So eigenvalue equation, this is operator O being applied to psi. Well, the result will have to be a constant O, lowercase o, times the original wave function psi. And this small o is the eigenvalue, and this psi is the one of the eigenfunction of this O operator. Postulate 4. So what if you have a wave function of a particle that is not an eigenfunction of this O operator? For example, x is not an eigenfunction of the position operator x. So if you apply x operator to x, you get x squared, and x squared is not a constant times the original wave function x. Therefore, we cannot determine the exact position of the particle with a wave function x. Then how do we actually have any kind of understanding about the position of that wave function or that particle? It's very simple. We somehow can obtain the expectation value of that position. So the more general equation is this. The expectation value of this property O, for example, the position, can be obtained by evaluating two integrals, one on top, one on the bottom. If you look at the bottom, it's simply the integral of the probability density. On top, It's similar, but you have to insert this operator O between the complex conjugate of psi and the wave function psi. Again, you evaluate these two integrals, and then we do a division. So in statistics, you see similar equations, but this corresponds to the probability weighted property of O in statistics. And if you view this psi star times psi as the probability density, and psi star times psi times d tau as the probability of finding the particle within the volume element d tau, you will better understand this equation. Postulate 4 also tells us if it happens that this psi is an eigenfunction of the operator O, and we have O being applied to psi, we get a constant lowercase o times psi, and then the expectation value of O can be derived easily by replacing this O psi with this lowercase o psi, in which this O is a constant, and the result is simply O. So basically it means if the wave function psi is an eigenfunction of the O operator, the expectation value is simply the eigenvalue correspond to this eigenfunction psi. Postulate 5, this is the time-dependent Schrodinger equation. If you apply the total energy operator to a wave function psi, the result is I times h bar times the first derivative of the wave function with respect to time. This h is Hamiltonian. It includes the kinetic energy operator and potential energy operator. In postulate 6, it says wave functions must change sign under the exchange of two electrons or any two other fermions. And the mathematical equation is very simple if we exchange electron 1 and electron 2. So now I'm putting 2 in front of 1, so I swap this 2, the sign must change. At any given time t, we can remove this t, and I'm using lowercase psi here, so psi of R1 and R2 is equal to negative psi R2 and R1. Over here, I swapped the two electrons. The famous Pauli exclusion principle results from this so-called anti-symmetry principle over here. If two electrons have exactly the same quantum states, that means if they have exactly the same spatial orbitals and spin state, we have psi of R1 and R2 equals psi of R2 and R1. That means these two electrons have the same quantum state. Imagine in a helium, we have two alpha electrons occupying the 1s orbital. So we have 1s alpha and 1s alpha. And then if you look at this wave function, if the two electrons are occupying exactly the same spatial orbital, 1s orbital, with exactly the same spin, both alpha spin, and we have this equation here. The quantum mechanical postulate 6 tells us if we swap two electrons, the sign must change. So in this equation, we have one additional negative sign here. What does that tell you? It tells us the wave function psi of electron 1 and electron 2 is equal to negative psi of this electron and electron 2. So this guy is equal to negative this equals to negative this. And for a wave function to be equal to negative that wave function, it has to be 0. That means the probability density will have to be 0. The result is that we cannot observe such a system with a 0 probability density, and it tells us it's impossible to observe two alpha electrons occupy the same 1s orbital in the helium atom.